In physics, we like to quantify the universe. We like to do calculations. We like to figure out numbers. We like to know how much, not just what's happening, but how much of a thing is happening. In physics, when we do calculations for acceleration, we define acceleration as the change in velocity over time. How quickly does the velocity change? That is acceleration. This is a lot to write out on a page though, so we use symbols and we have an equation. Here's the equation. Acceleration equals change in velocity over time. That triangle there, that's the Greek letter delta, capital delta, and it means for us in physics, it means change in. So we don't have to write the whole word out, we just say delta, change in. So change in velocity, the amount that the velocity changes, and then the time that it took for that velocity change to occur. This equation takes many different forms. Here's another form of this equation. In this version of the equation, we say A, acceleration, equals change in velocity, where V is the final velocity in the story that we've just learnt. U is the initial velocity in the story that we've learnt. So it's the difference between them. Final subtract initial. And T is the time that it took for the change to occur. In physics, when doing calculations, we follow conventions. These are conventions. These letters are the conventional letters that we use. We like to follow conventions in physics so that anyone else who looks at our work and reads our calculations can follow our reasoning and see if we've made a mistake. That way they'll know if they can trust our answers. Our definition for acceleration, which is change in velocity over time, can be rewritten in this format, which is very useful. In a story where something changes its velocity, experiences an acceleration, the final velocity of the object is equal to the initial velocity of the object plus the product of the acceleration and the time that it took to occur. Final velocity, meters per second. Initial velocity, meters per second. Acceleration, meters per second. Time, seconds. Example problem number 1. Julian is jogging at 2 meters per second. He accelerates at 1.5 meters per second for 2 seconds. What is the magnitude of his final velocity? In physics, we like to follow conventions when we answer questions. There are steps that we follow. The first step is we like to underline the important information. So for us, the important information is that his initial velocity is 2 meters per second. He accelerates at 1.5 meters per second. His time that he takes to do this is 2 seconds. We're looking for the magnitude of his final velocity. Velocity is a vector. It needs magnitude and direction. We're not being asked for the direction at this time. The direction is forwards, I guess. We're just looking for the magnitude. The next thing that we do in physics is we like to list our givens. So once we've listed our givens, initial velocity 2 meters per second, acceleration 1.5 meters per second, time 2 seconds, velocity is what we want to find out. We have a look, we see that all the units are appropriate. We can use these units, meters per second, seconds. We don't have to do any conversions. So then we show for the examiner which equation we're using. It is always important to show which equation you're using. The temptation is just to dive straight into the calculation, or worse, just give the answer only. That is not acceptable in physics. You must always declare the equation, show you're working, give your answer with units. We show our working out. So our initial velocity was 2. We got 1.5 multiplied by 2 for the acceleration multiplied by the time. And now we give our answer. The answer is 5, but we must not forget the units. The final velocity of Julian is 5 meters per second. That's example number 1. Acceleration calculation, example number 2. After a short sprint at 8 meters per second, Julian slows down by 2 meters per second for 3 seconds. What is the magnitude of his final velocity? So by convention, we like to underline the important information. Then we like to list our givens. We've listed our givens, and you'll notice that I've said that the initial velocity is 8 meters per second, positive. The time is 3 seconds, positive. But I've said that the acceleration is negative 2 meters per second per second. That's a negative value. He's slowing down. A diagram helps us to see what's going on. So in the diagram, we've got our Julian, he's running along, and we've indicated that to the right is positive, and we've indicated that to the left is negative. This is a situation where Julian's slowing down. We've said previously that acceleration is a vector, velocity is a vector. If they're in the same direction, then your object's going to be speeding up. If they're in opposite directions, then your object's going to be slowing down. Our acceleration is to the left. Our velocity is to the right. Julian is slowing down. Now let's declare the equation we're using. We always declare the equation we're using so the examiner can follow our reasoning. We place in our numbers, we show our working. You'll notice that I'm using brackets that helps me to keep track of what's going on, what's positive, what's negative. I always try to show the examiner what I have done as I work through the problem, so that if I do make a small mistake, I'll lose 1 mark, and hopefully my examiner will give me some follow-through marks for my good reasoning. In physics, we always like to show all of our working, so the examiner can follow our reasoning as we go through a problem. If you only put the answer and you get it wrong, you'll lose all the marks. If you show all of your working, including the givens, the equation, all your working, the answer, and the units, if you show everything, then the examiner might be able to award you some marks for good reasoning in physics, even though you might not have gotten the exact right answer at the end. Acceleration calculation example number 3. Julian enters the freeway at 54 kilometers an hour and accelerates for 5 seconds at 2 meters per second per second. What is the magnitude of his final velocity? Okay, conventions. Let's underline the important information. So the important information, Julian is traveling at 54 kilometers an hour. Kilometers an hour. We'll need to convert that to meters per second. He then accelerates for 5 seconds at 2 meters per second, and we want to know the magnitude of his final velocity. Let's list our givens. Julian enters the freeway at 54 kilometers an hour. We need to change that into meters per second. So we're going to divide it by 3.6. Julian's traveling at 15 meters per second as he enters the freeway. Now in the question we've said that Julian enters the freeway, he is accelerating at 2 meters per second, so it's safe to presume that his velocity, which is a vector, and his acceleration, which is a vector, are both in the same direction. So he's getting faster and faster. So I've made acceleration in this situation positive. I don't need a diagram for this. I'm going to declare my equation. I'm going to show all my working out. I get my final answer, 25 meters per second. And since his original velocity was in kilometers an hour, I'm going to convert this back to kilometers an hour. I recognize that 25 meters per second multiplied by 3.6 gives us 90 kilometers an hour. So we've got givens are listed, equation declared, show all working, give the answer, show your units. Sometimes in the question they'll actually ask you which units, or they'll actually tell you which units they want you to give it in. In this case, I've given it in meters per second and also in kilometers per hour. Acceleration calculation example number 4. Julian drops a ball from 2 meters. It bounces to a height of 1.25 meters in 0.5 seconds. Calculate the speed of the ball as it leaves the ground after bouncing. Okay, this is a more complicated question. What doesn't change though is we still underline the important information, list our givens, draw a diagram if we think it's a good idea, and then declare the equation. That's the important information. 2 meters, red herring, don't need that information. That happens before the story. The important part of the story is when the ball bounces up. That's before the ball even touches the ground. We're looking for the speed of the ball as it leaves the ground. That's at the start of the story. That's going to be our initial velocity. Let's list our givens. So we've listed our givens and we've put in a little diagram to help us to understand what's going on. The ball is dropped from 2 meters, it comes down, it hits the ground. This is where our story starts. It bounces back up at 1.25 meters. As it bounces up, its velocity, its initial velocity, which is what we're looking for, is up. The acceleration of the ball as it moves up, however, is down. Gravity pulls the ball down. The acceleration of the ball is down. And so we see a situation here where velocity, initial velocity, and acceleration, they're both vectors. Their directions are opposite to each other. So our ball slows down until it hits the peak height where it's not actually got any velocity at all. So zero velocity at the peak height before it would then start to descend. We want to know how fast was it going when it left the ground. Over here in our givens, we've identified that the initial velocity is what we are looking for. We did see from the question it took 0.5 seconds to reach this peak height. And I've written in that my acceleration is negative 9.8 meters per second. Negative because the acceleration is opposite to the direction of the initial velocity moving up. 9.8 because the acceleration of anything that is dropped on the surface of the Earth is always going to be 9.8 meters per second. At the peak, the velocity is 0. The final velocity at the peak of the bounce is 0 meters per second. Let's show our equation. Now we put in our values. We've entered our values. This is a more complicated question. It's not a simple plug and play. This is a more complicated equation. We know the final velocity. This time our unknown is on this side of the equation with all of these values. We want to get this by itself on one side of the equation. This is called isolating that variable. We want to isolate u on one side of the equation. So somehow we've got to get this over there. Let's do our next line of working out. Negative 9.8 multiplied by 0.5 is negative 4.9. I still want to isolate u. I want to get u by itself on one side of the equation. How can I do this? Well, I've got minus 4.9 here. So what I can do to make this move onto that side of the equation, I can add 4.9 to both sides of the equation. If I add 4.9 to both sides of the equation, then this equality holds true. Because with an equality, what you do to the left, you must do to the right. If I add 4.9 over here to make that disappear, then I must add 4.9 over there. Once the equality is held, I can then go through with the rest of my working out. 4.9, negative 4.9 plus 4.9, they're gone, and I'm left with the initial speed of the ball as it bounces up off the ground, 4.9 meters per second. Acceleration calculation, example number 5. Julian races his motorbike at his local racetrack. He is moving at 144 kilometers an hour when he applies his brakes for 6 seconds, slowing down to 90 kilometers an hour. Calculate his deceleration. Let's list the important information. So he's traveling at 144 kilometers an hour, so we know that that means we're going to need to convert that to meters per second. He applies the brakes, so he's slowing down for 6 seconds. The acceleration is going to be a negative value. His final velocity is 90 kilometers an hour. We need to figure out his deceleration. Let's list our givens. So we've got our givens. Julian's moving at 144 kilometers an hour. We divide that by 3.6 to get 40 meters per second. Julian has a final velocity of 90 kilometers an hour. Divide that by 3.6 to get 25 meters per second. He applied his brake for 6 seconds. We want to know what his acceleration is. We know his initial velocity is to the right, his acceleration is to the left. If we say that to the right is positive, to the left is negative, that indicates to us that his acceleration is negative. He is slowing down. Let's show our equation. So now it comes time to showing which equation we want to use for this equation. We could have used v equals u plus at, but we might go back to the definition of acceleration. Values for this one. We end up with 25 minus 40, we get negative 15, and a final answer of negative 2.5 meters per second, the negative indicating that it is to the left. Let's plug in our values. So we find ourselves in the situation again where our unknown value is not isolated. We can only find this out if we isolate A. So we need the 40 to disappear. For many of you in the room, you'll say, okay, well, I'll just bring it to this side and say 25 minus 40. I'm going to throw in the extra step just to make sure everyone else understands. If I want this 40 to disappear, I have to subtract 40 from this side. Because it's an equality, then I must subtract 40 from that side as well. So now I've got minus 40 on this side, minus 40 on that side. What does that give us? So I'm left with 25 minus 40 equals 6a, which gives us negative 15 equals 6a. I want to isolate a, so how do I isolate a in this situation? I divide both sides by 6, and that will isolate a. And I'm left with the acceleration being equal to negative 2.5. And I remember to put in the units, negative 2.5 meters per second, which indicates to us that the acceleration is to the left at 2.5 meters per second. Okay, so that's 5 examples of calculations for the acceleration equation. I hope this was useful for you.